All right, so just another quick comment on fission versus fusion, then we're going to be talking about uses of radioisotopes. So you can jot this down underneath the chart that you have filled out after the reading pages 810, 811, and 813. Both fission and fusion are nuclear reactions. Both fission and fusion involve converting mass into energy. All nuclear reactions do that. This is just a little bit of a reminder. All nuclear reactions will do that. They turn a little bit of mass into a huge amount of energy. The mass of your reactants will always be slightly greater than the mass of your products because of this loss of energy. So this occurs too with fission and fusion and transmutation. That's what we call that mass defect. So just that reminder that with all of our nuclear reactions, even with fission and fusion, which we've just been talking about, that we'll have we're turning mass into energy. We're losing a tiny bit of mass and turning into a tremendous amount of energy. The amount of energy we get from nuclear reactions is so much bigger than the amount of energy we get from any other type of chemical reaction. So uses of radiation. There are many uses of radiation. There are three that we're going to be discussing, three broad categories. Dating, by that I don't mean boy, girl, but more like geological dating, medical uses, and nuclear power. So with dating, we're using naturally occurring radioisotopes to determine, like, how old is this fossil, how old is this rock, how old is this anthropological sample we found, etc., etc., etc. But it's naturally occurring radioisotopes. So we're not using artificial radioisotopes here, like uranium or plutonium. It would be things like carbon. And it's the way that that is done, that the dating is done, is they use the ratios of one isotope to another to determine the age. So they essentially look at how much of each isotope they have, and then they compare the amounts to one another. And through that comparison, they can actually calculate how old the sample is. So this uses natural radioisotopes, but these radioisotopes have to have very long half-lives because we're talking about dating things. So basically this thing has to be radioactive for a very long period of time. That's what that half-life is getting at. So for example, carbon-14. Carbon-14 is the big one that I want you to know about dating, that it's used to date fossils and biological samples that are incredibly old. But the half-life of carbon-14, I know in your reference table it has a slightly different value from this, but it's on the order of 5,700 years. That means that half of the radiation, after 5,700 years, it will be half as radioactive as it was initially. But that's a really long time for half of the radiation to go away. So it allows us to date things that are very old. So carbon-14, what do I want you to know? I want you to know that it's used for dating purposes. Next up is medical. Radiation is used in two ways in medicine. It's used to both diagnose a disease, and it's also used to treat a disease. Many different types of diseases are used with radiation, cancer being a really big one. Radiation is used to both diagnose cancers and treat cancers. The way it typically works is you pick an isotope that will be sort of natural, an element, an isotope, and meaning a specific element that will go to a certain part of the body just by the fact of what the element is. And then if you make that element radioactive, then you can actually visualize that that area of the body. You can the doctors can sort of see what's going on. On the other hand, if you're using it to treat a disease, then you can send in a radioisotope again to a specific area of the body. And the fact that it's radioactive might be killing the cancer cells, and it might also be killing the healthy cells as well. That's part of the problem with chemotherapy. But that radiation can help to sort of attack the bad things that are going on in the body. When we're talking about radiation for medical purposes, we're using radioisotopes that have very short half-lives because we don't want them to stay in the body longer than they need to. So that's a really big difference here when we're talking about medicine. We are no longer talking about things that are radioactive for 5,700 years. We're talking about things that are radioactive for maybe a few hours, maybe a day, maybe a few days, maybe even on the order of minutes. Things with much shorter half-lives, so they're not radioactive as long. The big example that the Regents loves to ask in specific regard to this type of use of radiation is iodine-131 for thyroid problems. because there's a lot of iodine that needs to be taken into your thyroid gland for use. And so this radioactive form of iodine, iodine-131, is very useful for diagnosing thyroid problems, because this, again, this radioactive isotope just kind of will naturally go to the thyroid on its own, and you can sort of, and doctors can then see what's going on. Now, the half-life of iodine-131 is pretty short. It's only 8 days. So it's only going to be radioactive for, it's going to take 8 days for half of the radioactivity to go away. And then last use of nuclear power that we're going to be discussing is last use of radioactivity is nuclear power, and this uses unstable radioisotopes to generate energy. So this is fission, basically. So these are using our very large, very unstable radioisotopes that have incredibly long half-lives. Now remember, our large radioisotopes, these are uranium and plutonium. The big problem, so this is basically about energy generation. The big problem with this use of radioactivity is that their half-lives are so long. What do you do with this when you're done using it? The storage of waste is a huge problem. I mean, where do you put it when you're done? It's still going to be radioactive. It's going to be radioactive for 10 to the 9th years. I mean, this is a huge issue. Exposure of workers to the radiation and the length of time it takes for this radiation to go away. You know, what do we do with that? That's really tough. So, skipping that, again, all nuclear reactions produce massive amounts of energy, fission, fusion, transmutation, because mass gets converted to energy. And right now, please read pages 16 to 17 in your notes and answer the questions on pages 18 to 19 on uses of radiation.